Okay, in this video, we're simply going to state and prove the triangle inequality. So the triangle inequality says if you're given 3 points, A, B, and C, that AB, that's the length of the segment AB, plus the length of segment BC is greater than what? Well, if we look at this triangle down here that I labeled, go A to B plus B to C, that must be greater than or equal to AC. That is the triangle inequality. But when does equality hold? When would that be an equal sign? Well, that will happen, but only when A, B, and C are collinear and B is in between A and C. So in that case, you have the distance from A to B plus the distance from B to C is equal to the distance from A to C. And only in this case will it be equal. So we're going to do this proof in 2 steps. The first case will be if the points A, B, and C are collinear. And then the otherwise case will be the points are not collinear. So we're going to prove it here and here. So first, let's do the collinear case. Well, by the ruler postulate, if they are collinear, we have 3 possibilities. One is A dash B dash C. In other words, B is in between A and C. And this could have been written, I'll just write this once. It could have been written like that. That means the same thing. B is in between A and C. I won't do that for all the rest of them, but it could be that A is in the middle. BAC, which is the same as writing C dash A dash B. And then the third one would be C in the middle, like that. So we're going to consider each one of those cases. If B is in the center, then by definition of being in between A and C, I didn't mean to say in the center, if B is in between A and C, then by definition we have that AB plus BC is equal to AC. That's the definition for betweenness of points. This is the only case where equality holds. Okay, so suppose that isn't the case. Suppose it's A in the middle. That means that BA plus AC equals BC. All right, by the definition of betweenness. Thus, BC is bigger than AC, because here's BC, and on the BC is equal to AC plus another positive number. So BC is greater than AC, and therefore AB plus BC is bigger than AC. All right, so far we're good. If you have BCA, that means that BC plus CA is equal to BA by the definition of betweenness. Thus, AB is greater than AC. That's because AB is right here. BA is equal to AB. And it's bigger than CA because it's CA plus another positive number. And therefore we get AB plus BC is greater than AC. In all 3 cases, we showed that AB plus BC is greater than or equal to AC. In the first one, it was equal, and in the other 2, it was a strictly greater. So that's the end of the case 1 where they're collinear. Now let's go to the case where it's an actual triangle and they're not collinear. All right. So I'll need this picture. We're gonna construct something else from this triangle. We will prove that AB plus BC is greater than AC. So that distance, AB plus BC, is greater than that. All right, consider ABC, that triangle, and the point D on the ray CB. So it's going to continue that way. That's the ray CB, where B is between C and D, and BD equals BA. So let's see. Here's BA. I need to put D over here so that this length is the same as the length from B to D. So I'll guess that it's right about there, like that. Okay, so this length is the same as that length. That and that. We can do that again by the segment construction theorem. Now we're going to draw AD. This will make another triangle. And by the way, it's an isosceles triangle because we've got two equal sides. It says to label angle D as angle 1, label DAB as angle 2, and then label BAC as angle 3. BAC as angle 3, respectively. All right, so far so good. Now, observe that angle 1 is congruent to what? Well, this is an isosceles triangle. Your equal length sides here. So the base angles 1 and 2 are equal. Angle 1 and angle 2 are congruent. That's because ABD is isosceles. So the two base angles are congruent. And then part 4, by betweenness, we've got the measure of DAC angle. DAC can be broken up into this angle plus this angle. So the measure of angle 2 plus the measure of angle 3. So obviously, the measure of angle DAC is bigger than the measure of angle 2 because it's equal to the measure of angle 2 plus another positive number. Okay, now part B. By part 3, let's see, DAC is greater than the measure of angle 1. Is that correct? 1, 2, 3. Yeah, it's actually by measure of angle 1 and is congruent to the measure of angle 2. And since this is greater than the measure of angle 2, it's greater than the measure of angle 1. So we really used 3 and 4 to get this. So by the scalene inequality, that gives us that their opposite sides are in the same inequality, so to speak. The opposite side, CD, is greater than the opposite side, AC. By the scalene inequality. This angle is bigger than this angle, so this angle's opposite side is greater than this angle's opposite side. All right? Since CD is equal to BD plus BC, CD is BD plus BC, we can see that BD D plus BC is greater than AC. All right, because why? All I did is substitute CD greater than AC with this. This is another way of saying CD. BD plus BC. So that was by substitution. Therefore, since AB and DB or BD are equal to each other, we can substitute again, and I would get AB plus BC is greater than AC, because these two right here are equal. BD is equal to AB. So that was what we were trying to prove. AB plus BC is greater than AC. That's the triangle inequality. That's the end of the proof.